Hi, everyone. My name is Ioana Boier. I am an applied researcher in financial services with NVIDIA. And today I'm going to talk about large language models. And I changed a little bit the title of my presentation because I think when we speak of models with hundreds of billions or even trillion parameters, they may seem a little bit like modern day dragons. So they're certainly very opaque, huge neural networks, and we somehow are able to tame them into generating useful information. So the goal of my talk today is to highlight some of the challenges of working with language models and also to discuss whether we train the models from scratch, we use pre-trained models, and also look at some examples. So the agenda for today is pretty straightforward. We start with speaking about training large language models, which will lead us to foundation models. Then we talk about how to refine these foundation models to perform specific tasks, so customization techniques. And then after that, talk about some applications specifically to quant finance. Now, before we start talking about training, I just wanted to do a quick recap of the architecture that started it all, right? So I think large language models owe their phenomenal success in great part thanks to transformers, which were introduced in 2017 in a paper that was titled "Attention is All You Need." And on the left-hand side, you see the catalog and the timeline showing an incredible growth in popularity of this architecture after it came out. It's been adopted with various modifications for a number of applications, various tasks, even modalities, right? It's not just transformers for text or for natural language, but also for images, for video, and even for financial data. Now, the original paper actually focused on a translation task. I believe it was English to German. But the generalization properties of this particular architecture became very quickly evident to a lot of people. And also the fact that this particular architecture, with the way it's organized, with the dot products and matrix operations that are involved in the inner computations, renders itself very well to acceleration using GPUs. So our latest version of the GPU, for example, the NVIDIA H100, is supporting transformers specifically through a transformer engine that has additional built-in hardware support for accelerating transformers. Now, as far as foundation models are concerned, right, they are at the core of the LLM discussion nowadays. And you may wonder, like, what is a foundation model? And I put here the definition that Stanford has, which is, well, actually at Stanford, there is the Center for Foundation Models. And they are defining foundation models as those models that are trained on generic data, and then they can be adapted after training. So once the model has been pre-trained, to a wide range of tasks. And this is interesting, right? Because it's a paradigm shift from having one model per task. So one model to summarize, one model to translate, one model to write stories, to having a foundation model that's pre-trained on a variety of data. And then this model is being refined for the specific tasks, right? And nowadays you can find some of these pre-trained models freely available, whether on GitHub or in repositories like Hugging Face, the NVIDIA NGC, and a number of others. Or you may know of such models that exist, but are not necessarily downloadable as checkpointed models, right? So ChatGPT, for example, is a foundation model that you can access perhaps through a API, a programmatic API, or through the web interface, but it's not something that you can download and use directly from the model weights. Now, the next thing to think about when we use large language models in production are how, what's the best way to maintain and deploy these large language models, right? Once we've built them. And this is not a trivial task. Now, there are many use cases that come out every day, like in all areas of life, but in finance specifically, whether, for example, we want to use large language models in conjunction with proprietary firm data for question answering, for summarization, for different kinds of sentiment analysis of things that are happening in the market, for engineering and development purposes, risk management, compliance. I mean, there's many, many use cases in finance, but I think there's still many questions regarding the best practices when it comes to using the large language models. Should we train the model from scratch? Is it better to download a pre-trained model and then refine it? What size model do we need? What does size even mean? Is it more parameters, longer context? What types of refinements should one use for specific tasks? So this is there are a lot of questions, and there are questions that are not trivial to answer. So we'll try to go through some of them today. So first, let's look at model training, right? I mean, training from scratch poses some very, very serious technical challenges, right? So first of all, just the first step, assembling the right data, it's by itself a big endeavor, right? Not only you need to have the data collected and then processed and cleaned up, but it also needs to be representative of all the things that you want to do with the models later on. And then also you have to think of non-technical things, like, for example, having the right licenses for the data, or having the right, or what happens if that data that's currently free becomes not free in the future, right? Like some of these companies that found their data used for training purposes have announced that they will start charging for it in the future, right? So it's kind of interesting, and how does that affect a model that's in production, right? And it's also a question, for example, if you, what's the best way that you train the model on generic data and then refine it with domain-specific data, or is it that you mix generic data with domain-specific data and then train, right? So these are questions that are, some of them are empirical questions, right? Like this last one, and they're not really that easy to answer, because in part, the experiments and the training itself is actually very compute intensive, right? These models, and in this example, I'm showing here 175 billion parameter model, like a GPT-3-like model that requires not only a lot of compute power, but also a lot of memory for storing the different parameters, gradients, different states of the model, right? So in order to make the training feasible, we have to take advantage of not only data parallelism, but also model parallelism. So one way to do that is shown in this paper that I've linked here. And also there is a GitHub associated with it. It contains our Megatron code base, which is capable of efficiently training very large models, taking advantage of these notions of data parallelism and model parallelism. And it explains how you can leverage distributed computing on thousands of GPUs by running examples of models from 1 billion parameter all the way up to 10 billion, to a trillion. There are 10 models in total, right? And it shows that you can achieve near linear scaling in terms of the petaflops achieved as a function of the number of GPUs used. And in terms of the different kinds of parallelism, right? Like the data parallelism means that you're splitting a training mini batch across multiple workers, but then you cannot you just do data parallelism, right? So it's not that data is the only thing that's massive. The model itself is massive, and so the memory usage of the model and the computation of the model have to be distributed. And so this is these different notions of parallelism. How do you chunk the model into pieces, whether you use this interlayer parallelism or intralayer parallelism, right? So pipeline versus tensor parallelism. So these are all questions that you have to ask yourself when you're training the model. One interesting thing here is that this kind of choice is just one type of, or a couple of types of hyperparameters on which you have to make a decision for training. And this brings up another very compute-intensive, potentially compute-intensive consideration, which is what are the optimal hyperparameters to train your model? Our repository contains tools, for example, like a hyperparameter tool that allows you to find optimal configurations without really having to search the entire hyperparameter space, because that's essentially a prohibitive calculations if you have to run the model every time and see how it performs and then compare it to the next run and so on. Once you have a trained model, whether you pre-trained it, whether you trained it yourself, or whether it's something that you've downloaded from somewhere, it's a question of also how do you use it? How do you keep it up to date? And there are a number of things that have to do with that, right? Like, so, like we said, we talked about the data licensing and all of that. But also the data can become quickly outdated. If you remember ChatGPT, when it came out, it said that the data that it was trained on was used up until 2021, I believe, right? So that means that everything after that date is not part of the model training, and so the model is actually not aware of anything that may have happened after that. These language models are generative in nature, so there is this other issue with them, which is some people term it hallucination. Other people talk about the alignment problem. But in essence, they learn data distributions and produce plausible answers, but they're not necessarily factual answers, right? So this brings us to the next discussion, which is actually taming our dragon, right? If you take a generative model like GPT and you're asking it to perform a certain task, you won't know what that task means. It just knows to predict, given a sequence of tokens, it will predict the next token. So in this example, for example, in my colleague Ioana's, he was talking about standard C++. So this is an example that I highly encourage people to try out. But this is an example where I give it a, let's say, a C++ sequential codes, like old style C++, and then I'm asking the model to translate between old style C++ and the standard parallelism that's available in ISO C++ 17 and later. And of course, if we send this kind of request to a pre-trained model, it won't know what that means. But once the model is customized to do, for example, code translation, and this can be done between different languages or within the same languages, between different styles, right? Like, or any task, right? Whether it's summarization or Q&A or other things like that. Once you've refined the model, once you've customized the model, then of course that's possible. So let's talk a little bit about some customization techniques. I think there are broadly two main categories of customization methods: fine-tuning and parameter efficient tuning. And then within each category or each class, there are a number of techniques. And I'm not going to go into detail of all of these techniques. However, throughout the presentation, I have links to materials that you can download for free. And these come in the form of either papers, videos, blogs that are available for you to dig deeper into the details. All right, so let's see, fine-tuning. This is something that can be done on either all or just some of the layers of a neural network. Of course, if you do it on all the layers, so retraining the model, the pre-trained model with additional data, by allowing all the weights in all the layers to change. So full fine-tuning performs best. But the downside is that it's expensive, and it can also be very prone to overfitting. And this can be done in various ways. It can be done for a single task, for several tasks. It can be combined with something like reinforcement learning with human feedback, which is a combination of the language models with a reward model that's trained using human feedback, and then it's used as a reward function for the language model. So it's essentially learning to do like a classification of like good answer versus bad answer. And this is especially useful when it's kind of nuanced to detect of what, when you have a more complex type of task or output, or also when you want to align that output with human preferences, right? And of course, the downside of this is that it's human feedback, so it can be expensive, and it's also not necessarily very scalable. Parameter efficient tuning means that you're trying to be more efficient in terms of what gets adapted given a pre-trained model, right? And so that means that most of the weights are going to be kept frozen, so you're not retraining all the parameters, only a small subset of those, right? And examples in this category include the ones that I've listed here, like prompt tuning, p-tuning, adapters, so on and so forth, right? And so let's look at a couple of them. Prompt tuning, for example. So on the right-hand side, we see the main components of a large language model. So what you need to train a large language model, that's in blue. And essentially it takes as input a set of tokens. So this could be like specific to the task. Like, for example, if you have reading comprehension, it'll have a paragraph and then a question, right? And then you have an answer to that question. And, based on that paragraph, you could have classification, something like that, right? Or something more creative, like write a story or write a poem in haiku style, things like that. These inputs are then converted to vector embeddings, and these are processed by the large language models. And so in prompt tuning, there are some additional virtual embeddings introduced so that these are being trained to be specific to the task. So for example, they are initialized with random values, and then during the training, they're the only ones that change. And the prompts can be, all sorts of things. It can be cues, it can be words introduced by humans, or it can be AI-generated numbers introduced into the model's embedding layer. P-tuning is another example. It's a slight modification of the prompt tuning, right, where the virtual embeddings are now passed through a small neural network. This is typically like an LSTM type of network, but it's much, much smaller than the network of the entire language model, right? So it turns out that adding and training this small network in addition, while keeping the whole part that's in blue fixed, is actually very effective for a variety of tasks and with relatively little data. So you don't need that much data in order to achieve good performance with these techniques. And then there are a number of other techniques that you can check out at this link. So now that you have, let's say, a fine-tuned model for a particular task, then you can, let's say it's question answering or something else, then comes the question of how good is the model to respond with not only plausible responses, but actually calibrated or fact-checked responses, right? And the answer is not particularly. It can be quite bad. In this example, I'm asking a question that relates to a particular book and the book's author. And of course, there's no space for creativity here in the sense that the author is the author, right? So you would like the model to know that and to answer with the author's name. And I think it does a very good job in terms of being plausible, like it comes up with a name, but it's not the right name. So when you iterate with it, then it corrects itself, maybe bringing up the next most plausible thing. And in this case, it's correct. The author's name is Kazuo Ishiguro. However, some other mistakes are being made in the process, right? Like he's not Japanese American, he's British American. And then this notion of him being a professor, right? Like I actually Googled, I didn't know. So if you don't know what the answer is, it's actually interesting that these models may tell you something that you could believe, but it may not necessarily be true. So I looked at it, and it turns out that the word professor comes out a lot in Google searches associated in the same context with the name of this author, simply because a lot of professors in academia have studied his works. So one solution here is to, for example, augment the large language model with retrieval from a large database, right? And this is the example that was the example that I have on the right references a paper called Retrieval Enhanced Transformers. And what's interesting here is that it not only helps with guiding the model and making it more factual, but it also helps with the explainability. Because when you're able to not only give an answer, but also point to the paragraph where you've extracted that answer from, this becomes actually much more useful. I think it looks like I'm running out of time. So I'm going to stop here. The presentation is available, and feel free to reach out to me in LinkedIn, or if you have any questions. I'm going to introduce the next speaker. That is my colleague, Maxine. And Maxine, please take it over.